Okay, so just a quick recap. I've implemented an indicator that predicts microprice movements using a convolutional neural network trained on Orderbook data. We need to collect our own data, transform, and use the TensorFlow Keras library in Python to construct a convolutional neural network model. And the fitter of the trained model would then be used to predict if the prices will increase or decrease in the next 30 seconds or so in JavaScript. The prediction is executed in JavaScript so that it can be more easily integrated into a web app to show predictions live in the browser by calling the exchange's Orderbook API. Let's take a look at the code in more details. First, we need to collect the Orderbook data. I've decided to pull the data from Binance. To save space, the raw Orderbook data is summarized into the total size per price point and separate files on a daily basis. A WebSocket approach would be more, in theory, more comprehensive, but it's less practical and much more challenging to work with. Once we have the order book data stored, we need to transform and normalize it. The various prices in the order book are converted to 10 times the 0.1% delta categories, covering price movements from -1% to 1% from the last traded price. Each price category has 4 features, basically bid price, bid size, ask size, and the size and the limit orders are normalized by finding the mean and standard deviations and calculating the z-value or the standard score. The data is split into training and validation sets in the ratio of 80 to 20, and daily files are also combined into one large data set. Once we've got the data collected and prepared in parallel, let's look at the model. First, make sure you have your GPU configuration set up and TensorFlow Keras libraries imported. According to the TensorFlow documentation, mixed precision using float16 type specifications makes training models significantly faster, but not all GPUs support this stuff. Here we specify the data sources, and we set up the time frame of the sample or historical data to be 300 seconds, and to predict the direction of the price in or by the end of the next 30 seconds. The feature column is 40 because we have 10 times the 0.1% delta, and within each level, we have bid price, bid size, ask size. So it's 300 by 40. The research paper used 100 by 40, and a difference is that it's 100 samples, not seconds. I chose to collect the data in seconds instead of number of samples because that seemed to make more sense to me. Although, admittedly, I think it does miss out some of the intra-second movements. Batch size is GPU memory specific. The more GPU RAM, the more batches you can shove into memory for each epoch run. In this model, there'll be 200 epochs, or runs or cycles iterations of model fit, each defined by one forward pass and one backward pass to be performed. You want as much data as you can in the GPU RAM rather than in the system RAM because it will ensure your GPU cores are fully utilized. We set up a checkpoint after each epoch to save the model in the callback function later on. We also need to define a data generator class to further prepare the data from the data collection bar. This is because overlapping windows of 300 samples are required to be fed into the model. So if you've got 1 day of data, and that's about 86,400 seconds, there will be 86,400 minus 300 also windows of 300 seconds each. This should also be done mostly in memory, with batch size specified, but this step involves mainly the CPU and the system memory. It will likely use up all your system RAM, but it will be much faster than paging by even SSD drives. The Y and predictor variables is set into 3 categories: price up, price down, and price to stay the same. We need to ensure the categories are balanced to make sure that the model also pays attention to underrepresented categories in the data. Next, the model is defined. I've pretty much followed the paper's design and its parameters. Feel free to check out the paper for more details. In this model summary, let's take a look at our dimensions and tensors in each layer. In the first layer, because our stride is 1 by 2, basically groups the price and size data for each bid and ask. And 40 features of bid price, bid size, ask price, and ask size are reduced to transform the information to 10 bids and 10 asks. 16 channels are created from 16 kernels. Given the kernel is 1 by 2, so 2 parameters each, and we typically add a bias parameter, that's 3 parameters now, for each channel. And 3 times 16 channels give us 48 parameters. In the next layer, we would maintain the X, Y, and Z dimensions, and the kernel for each of the 16 input layers is 4 by 1. The 4 is basically smoothing over time, creating a moving average using a window of 4 seconds on the input data. So if we take 16 channels times the 4 by 1, add 1 bias, that's 65 parameters. But we also have 16 output channels, so 65 times 16 is 1040 parameters. In order to capture the temporal relationship that exists in the extracted feature, we replace the fully connected layers with LSTM units. The activation of a LSTM unit is fed back to itself, and the memory of past activation is kept with a separate set of weights so that the temporal dynamics of our features can be modeled. The callback is triggered to save the model after each epoch. You can check the accuracy increasing after each epoch. For the validation set as well, it tends to stabilize around 75% using this setup. Once we've got the model saved, and you can see some examples here, we can load the model, which was all done in Python, into a JavaScript file for live testing. The idea of using JavaScript is that it can then be more easily integrated into a web app for predicting. In this file, the orderbook is directly requested from the Exchange API and formatted and passed through the model every second. After 300 seconds or so, there will be enough data to start predicting the price movement. If the prediction is correct, a score of 1 is logged, otherwise a score of 0 is logged. That's it. Thank you for making it this far, and I hope you liked the walkthrough. Definitely read the paper if you're interested in the topic. There are also similar ones out there, so happy researching. In the next video, I will talk about some of the personal experience in making the indicator and the challenges that I faced. See you there.